this is a car. Well, it's not a real. Actually, technically, it's a real car. So if you've been in a car before, which is very likely, you don't even have to drive it, and you're getting from one interstate to another, and you take that curved on ramp. They're usually not flat, but banked a little bit. It turns out that there's a bank angle that is ideal such that you don't need any friction between your car and the road in order to make that turn. And that's what we're going to calculate. So let's just review really quickly, because in a normal flat curve, then the car is going around a curve. What force makes it move in a circle? There has to be a sideways pushing force, and that would be the friction between the wheels and the road. But if you bank it, you don't need a frictional force, and that's what we're going to calculate. So I have here, the problem said a curve with a radius of 1.2 kilometers or kilometers, and the velocity of 105 kilometers per hour. Let's just go ahead and convert that to meters per second, because that's going to make everything easier. We need to do that because we're going to have G in there. G is in newtons per kilogram, which is a meter per second squared, so I can't use kilometers per hour. Okay, so I have 105 kilometers per hour. I want to convert that to meters per second. So there are 1,000 meters in 1 kilometer. That's what that means, right? So the kilometers cancel. And then I need to convert hours to seconds. So I'm going to just go ahead and say in 1 hour, there's 3,600 seconds. And you could convert to minutes first, but there's 60 seconds in a minute, and there's 60 minutes an hour. 60 times 60 is 3,600. So if I do that, I get a velocity of 105 1,000 times. Yeah. I didn't know why I did that. 3,600 divided by. I get 29.2. Let's go 29.17 meters per second. So that's my velocity. Okay. Great. Got it. Now let's draw a free body diagram for our car at this position. So remember, if you think about it from the top view, here's my car. It's coming down this way. So we're looking at it coming out of the page this way. And there's some force pushing towards the center of the circle in order to make it to move in a center towards the circle. Okay, so my center of the circle is over here. So let's just draw the force diagram. What force do I have? Well, I know I have a downward gravitational force. And then here's my road at some angle theta. And so I also have a normal force. And the normal force is perpendicular to this. Now, what other forces are acting on the car? And the answer is, that's it. If it's an ideal situation and there's no friction, that's it, okay? Now, the next thing that we need to do is to choose our x and y axis. And you may say, hey, let's put the x-axis like down that way. We've done that before. Don't do that. Because if you do that, then the car is accelerating that way. That's the center of the circle, is that way, right? If I put the acceleration, the force is this way, it's going to have an acceleration in the x and the y direction, and I don't want that. I want an acceleration in just one direction, one component. Okay, so if that's the case, I need to figure out my angles here. Imagine that this plane goes down to 0, then this force would be in the vertical direction. So that can help me see, without having to do a lot of geometry, that that's the angle theta, and that's important. Okay, so I don't know n, I don't know theta. Let's just start writing down our forces. So I can say F net in the x direction is going to be the net force in the x direction is just a component of this normal force. It's this part up here, the opposite side. That will be equal to n sine theta. So remember, just because it's the x component doesn't mean it's cosine. You got to look at your picture. And that will be equal to the mass times the acceleration. It's moving in a circle, so we have centripetal acceleration. Remember, AC is v squared over r, so this is going to be equal to v squared over r. I don't know n, I don't know theta, I don't know m, I do know v, and I do know r. So I can't solve that for theta. Okay, but I have an equation. When you have an equation and you can't solve, the best thing to do is just keep carrying on and find another equation. So let's do that. F net in the y direction is going to be equal to 0. So that's the nice thing about choosing this for my x and y axis, is that the acceleration this way is 0. So I did a pretty good job there. Okay, so now in this case, I have two forces. I have this component of the normal force, which is the adjacent side to that right triangle. So we're going to use cosine, and then I have the gravitational force. So that will be N cosine theta minus mg equals 0. Now I still have three unknowns, right? I don't know m, I don't know m, I don't know theta, and I don't know n. And it looks like you can't solve it. But let's just do it anyway. Let's solve this for n and then plug it in up there. So if I add mg to both sides, n cosine theta equals mg. And now I'm going to divide both sides by cosine theta, which seems silly, but I'm going to. N equals mg over cosine theta. Now I can take this and substitute it in up there. So if I do that, I'm just going to erase this stuff. I need to work on my board space management protocol. Okay, so there's my equation. I'm going to substitute this in for n, and I get mg over cosine theta times sine theta equals m v squared over r, and we got lucky. Because now the mass cancels, and the only variable I don't know is theta. That's a double win. Double win. Okay. Double win. Okay. So I can do something else. I'm going to divide by g, and then I have sine over cosine. Sine divided by cosine is tangent. So this is going to be tangent theta equals v squared over gr. And I can solve for that. But let's just check first. So v is in meters per second, and I square that, I get meters squared per second squared. Down here I have meters per second squared times meters, which is meters squared per second squared. So this whole thing has no units. That's good, right? Because tangent theta is a ratio of sides, so it can't have any units. So this can't have any units. But then I can solve for theta. It's going to be the inverse tangent of v squared over g times r. Let's put in our numbers. I usually write it out, don't I? Okay, I'll write it out. So tangent inverse of v squared, so 29.17 squared over 9.8 times 1200. That's, I had to put this in meters to get everything to work. And make sure your calculator is in, well, it doesn't really matter. I'm going to use my calculator in degree mode because I like to think in degrees. So I have 29.17 squared, 9.8 divided by 1200 divided by, and then inverse tangent. Atan 4.14 degrees. So you don't have to bank it too much. And those, if you bank it too much, the problem is when you go too slow, you could slide down the bank. Okay. Now, if you want to find the bank angle and have friction, that's a pretty tough problem, but not impossible. But there you go. The end. Oh, let's say, notice that if I go faster, then I'm going to have a higher bank angle. Okay. If I make the radius of the radius of the curve smaller, I'm going to have a higher bank angle. The end.